Okay, so today we're going to talk about triangles again, because triangles are cool. They're everywhere, and if we look at them, we can learn a lot about the world. And today, we're going to talk about just one kind of triangle called a right triangle. And a right triangle, when I say right, I don't mean right and wrong. I don't mean left and right. I mean, in the language of math that involves shapes, a right angle, it's a perpendicular angle. So like between a flagpole and the ground, or between the walls and the ground, or the walls and the ceiling. It's the angle that's in every corner of a square. And if we look on our protractor, a right angle is just a 90-degree angle. Okay? Oh, and this little thing. When we're sketching shapes to solve math problems, and we're dealing with a right angle, we put a little quick in the corner here. That means this is a right angle. Then we don't have to, if our sketch is not very accurate and it doesn't really look like a right angle, and we put that there, everybody knows, oh, that's a 90-degree angle. Okay? So this is what I mean when I say right triangle. Right triangle is a triangle that has one corner that's 90 degrees, one perpendicular corner, one right angled corner. And it could be a really long skinny triangle like this with these two sides very different lengths, or it could be a right triangle that has two sides that are the exact same length like this. But we're going to talk about right triangles in general today, so let's think about them with two different sides, okay? And here's the question that we want to find the answer to today. Let's pretend that we have this triangle and we know this length. This length is length A here. And we know this length is length B here. So the question I want to answer today is, how do we know, if we know these two things, how do we know what C is? This longest side, the side that's opposite from the right angle. And this is a really useful thing to know, has lots of applications in the world. For instance, if we want to sail around the world, there's probably lots of applications if you're sailing around the world, but if we're going to sail around the world, first thing we need to do is build a sailboat, of course, right? So let's build our sailboat. Here's the hull with a little keel. It's not a great sailboat, but it'll do. And I've got a mast here, and the mast is at a right angle to the deck, yeah? And I designed this thing, and I built it, so I know that this length is length A, and I know that this length is length B, and it comes time to put on the sails, I need to buy some steel cable to run right here. And I need to know how long this is. Now I could just, I could shimmy up the mast and maybe take some duct tape and attach one end of a tape measure up there, and slide down the pole and walk up to the bow and measure it that way. But then, well, first of all, one end of my tape measure is duct taped to the top, and I have to go back up and get it, and that's a pain in the neck. And I'm a little bit out of shape, and so shimming up the mast is not a great or safe thing to do. And plus, I'm running out of time because the store, Steel Cable R Us, is closing, so I want to do this fast. But luckily, when I was in middle school, my teacher talked about right triangles, and I know how to do this. Okay, but I'm getting ahead of myself. You're still in middle school now, so this is what I want you to do. Set aside your sailboat for now, and take out your colored piece of paper that I gave you. And first I want you to fold it lengthwise, like so. Try to get the corners lined up nicely. You won't regret it. And then fold it and make a nice tight crease. Ta-da! Lovely. Then I want you to fold it the other way, like this. Okay. Nice crease. Now, what we're going to do is we're going to make a right triangle using that fold that's in the center of our paper. And in fact, what we're doing is we're making 4 exactly the same right triangles at the same time. Okay, so I'm going to draw a little line here like this. Take out my scissors and cut out my very boring snowflake, or very fabulous 4 triangles. Now, we don't have 4 triangles yet, we have a diamond, but that can easily be remedied if we cut along the folds that we just made, like so, and like so, and like so. Try to actually cut on the fold. That'll do, I think. Yep. But I cut my pen so it doesn't dry out. Now, I'm also going to get another piece of paper to work on here. So now, we have 4 triangles that are exactly the same shape. Yeah? Now I don't, we would just want to look at one side. We don't want any mirror images here, okay? So let's just look at them this way. And let's label our sides and make them all exactly the same. So have them pointed the same way so that you get this right. A. This is the shortest side. We're going to make A. The medium length side we're going to call B. And the side that we're especially interested in today, this longest side that's opposite the right angle, is C. C. Okay? Now, we know these are right angles in one corner, right? And we also know, by the way, that all squares have 4 right angled corners. So let's make a square with our 4, since we have 4 triangles. Isn't that convenient? Because we can make a square really easily. It's almost like I planned it. Alright. So try to get it lined up so it looks like a real square, shall we? That'll work more or less. Okay, and then just for fun, let's draw the square on the back paper. So let's put a little dot in each corner. Okay. Oh, try not to get rid of your paper. Just get the. We'll come back to you, triangles. We're not neglecting you. We're not leaving you for the square. We're just gonna draw a square real fast. Here we go. Okay, so here's our square. And let's put our triangles back in place and then look at this a bit, shall we? Oh yes, let's do, by all means. Okay, now notice we don't just have one square, we got another square, kind of cockeyed square in the middle, right? So I've got some questions about these 2 squares that I want to look at. First of all, what is the area of the inner square? Okay. Let's see. It's got 4 sides, like all squares, and one side is length C. And we know that if we take a rectangle, we can get the area by multiplying the length by the width. And a square is just the same thing, so we can call this area C squared, yeah? Question number 2. What is the area of the big outside square? Well, we've got a different side length, which is A plus B, right? And that's true on all sides. A plus B, A plus B, A plus B, A plus B. So that, if we square that, we get a plus b squared, yeah? And now, a third question is, what is the area? We know the area of this square in the middle. What about the triangles themselves? How much space are they taking up? And the easy way to figure that out is if we just put two of them together, we get a rectangle. And these two will do the same thing. And the rectangle is got side A and side B. So that rectangle is area AB. And we've got two of them. So we've got 2AB. So this is the area of the big square. This is the area of the triangles. This is very complicated math jargon to draw the little triangle there. So now I want you to notice that if I take the area of the inside square and I add it to the area of the triangles, c squared plus 2ab, I get the area of a plus b squared. So I can write that down. C squared plus 2ab equals a plus b squared. Now we get to do a little algebra, a little simplification. First of all, we're really interested in the c mainly. So I'm going to put that on one side of the equation. C squared equals, subtract 2ab from both sides, and I got a plus b squared minus 2ab, right? Then, oops, I need to put this, there we go. C squared equals, let's multiply this out, a squared plus 2ab, hey, that's going to come in handy, plus b squared minus 2ab. Time to easily simplify. Cross this out because there's a negative 2ab. Cross this out because there's a positive 2ab. They cancel each other out. And then we're left with c squared equals a squared plus b squared. Now, it just so happens that, wonder of wonders, this is what we need to know to figure out how much steel cable to buy for our sailboat. Right? Because let's just pretend this is the sail of the sailboat. Remember? Bow, base of the mast, top of the mast. This is the steel cable C. That's what we need to know. So, if we need to figure this out, all we have to do to find C is take the square root of both sides. It's the square root of a squared plus b squared. Okay? Now, what we've just done is proven a very famous rule in math. This c squared equals a squared plus b squared. This is called the Pythagorean Theorem. Do I have space to? Yeah, I can write that here. Pythagorean Theorem. It's named after a guy, a Greek guy who lived a long time ago called Pythagoras. And Pythagoras lived a little over 2,000 years ago in Greece. And we named this after him because, especially from a Western perspective, we think that he's the one who discovered this. He's really the one who made it famous. And really, he was really just the guy who got a bunch of people together, a bunch of mathematicians together to talk about this. And we don't know if he's the one who really got the idea to solve it or whether it was one of his buddies. The other thing is that we also have proof that the people of Mesopotamia knew about this more than 1,000 years before him. Mesopotamia is the ancient name of the land that's now mostly called Iraq, the place where America has fought a war for most of the last decade. There's also evidence that people in China knew about this before the Greeks. So, and I say this because I want you to remember that math and science do not just come from one part of the world. They are the knowledge of civilization, of human civilization everywhere. And even though European culture has dominated much of the world for a long time, Europe is just one of many sources for civilization. And there's more than one way to arrive at the truth. And in fact, I know of at least one website where they listed 90 different ways to prove this. There's lots of different ways to come to this conclusion. And actually, just in case you don't trust all this algebra stuff, I've got another way to show you right now. So, same question here. We're dealing with these two squares. What's another way to look at this? If you take these triangles and move them like this, and you're still trying to figure out what's the difference between the area of the big square, big and small. Let me just draw this. This will make it easier. Notice that we now have the space that's not covered with triangles. If you make a little dotted line here, hey, there's two squares here. And look at this. The side of this square is A, so this area is A squared. And the side of this square is B, so this area is B squared. And we already know that this same area that's not covered by the triangles, remember this area is C squared. Now, it's the same area, we just moved it around, right? So that means C squared, the area not covered by the yellow triangles, is equal to A squared plus B squared. You see? We get the same answer if we look at it this way. And this is just like one of 90 or probably more than 100 different ways to prove it. Okie dokie. So this is a very handy thing to know about right triangles, and I'm sure it will be useful in the future if you remember it. Oh, here's one more thing to know. One more word to know. Right triangles. Let's get a new piece of paper. One more thing to know, a little jargon for you. Right triangles. This C that we've been talking about so much has a special name. It's called the hypotenuse. And the hypotenuse is a short way of saying it's the side of the triangle that's directly across from the right angle. Yeah, but it's faster to say hypotenuse. So hypotenuse, we're gonna see that word a lot more. So that concludes my little introduction to Pythagoras and his theorem, which he's not the first one to have discovered. Okay. So the rule that you have to remember is that if you've got A, B, and C, C squared equals A squared plus B squared.